That's okay. I'm not actually sure how to click OK for that.
One, I'm happy to introduce Partner more relevant visiting us from Purdue University. He's interested in many cool things such as sublinear algorithms, learning and machine learning and statistics, and he has done significant work in all of these and even cryptography. He has a test of time award for his work on proofs of knowledge. And he's also interested in exotic things such as fluid dynamics and computational models, new computational models of the brain. And in his free time, he's a really good squash player, which I suspect is the reason he visited us to play with our own professional player, Cameron. So yeah, thanks. And today he's going to talk about this tantalizing problem, which is the trace frequency key.
Okay, yeah, thanks. Yes, I'm really happy to be here. This is my first time in Waterloo. I hope I'll be back, and not just to play squash, but also to talk to all of you. Yeah, no, I've known Elena for years. We were PhD students together, so yeah, I appreciate the invitation. Okay, so yeah, trace reconstruction. This is joint work with two of my students, Arnav and Hongao, and Zach Chase is not one of my students, and he just got a job at Rutgers. Yeah, let me tell you about this problem, and this is a work in progress. It's what I'm excited about, so I think it's more fun to give you a talk if you can sense the genuine excitement coming off me. So it's very much half finished. I hope you'll forgive some of that, but I hope to emphasize some intuition and some open avenues of progress on this. Okay, so I wrote the first half of these first half of the slides here for ITA, this information theory conference workshop. So introducing this a bit more from the information theory side. Kind of the most classic stuff, all originated around the founding of information theory, is you've got some n-bit message, you want to send it over some channel, and then the channel may corrupt the message, and then you want to recover the message afterwards. So what kind of channel are we talking about, and how well can you corrupt things? These are kind of the defining questions of information theory. The most basic channel is maybe the error channel, where each bit is flipped with probability p. So some random set of these bits indicated in yellow are flipped. And then after this, you want to figure out what's the capacity of the channel. How much information can you recover from this channel? So you maybe encode your message with an error-correcting code, send it through the channel. You send n bits across, and how many bits can you get out? N times 1 minus the entropy of p. So a maybe slightly less familiar channel is the erasure channel, where instead of flipping bits, each bit gets erased, replaced with an x. Okay, so is this better or worse? I don't know. It's a bit different. And again, very well-known classical analysis for this kind of stuff. Yeah, and just to say something trivial, so entropy is a kind of a bump-shaped function. So if you flip none of the bits, then you get all the information. But if you flip all the bits, you also get all the information, right? Whereas if you erase none of the bits, you have all the information. If you erase all the bits, you have none of the information. So they're just kind of different. But okay, it's the third channel, which is the subject of this talk, the deletion channel, which, yeah, so I don't know exactly the reason there's nomenclature, but deletion here is considered to be not replacing something with an X, but just blacking it out. Okay, so the deletion channel just removes some bits. You don't know which bits were removed. You only get a subset of the bits at the end of it. Okay, and how many bits of information can you recover from this? We don't know. So I mean, there's some good bounds here, but the thing which I'm going to talk about is a particular kind of simplification of this setting, which makes the our lack of knowledge even more acute, I think. So okay, I'm going to call a trace what comes out of this channel, and how many times we need to send some string X or maybe Y through this channel so that we can figure out at the end if it was X or Y that's being sent to us. Okay, so the game is either someone is sending X to us repeatedly or someone is sending Y to us repeatedly. How many times do we need to get a trace in order to distinguish X versus Y? Okay, um, so okay, this is actually a pretty easy game. The answer is one. The answer is one. Again, supposing someone flips each bit with probability P, so how would you win this game? Well, for the first channel, you would find any location in X and Y that have different bits, and you would just look at that bit and see if it's more likely to come from X or more likely to come from Y. And then you can just win this game with constant probability with just one trace. Okay. Same with erasure. You find one bit where these things differ, and if it's not erased, then you know exactly which string you're looking at. If it is erased, then okay, you failed with constant probability, but constant success probability is fine, you know? Okay, so the trace reconstruction problem is the last thing. And the point is that it's embarrassingly bad, the situation here. So we don't know whether it's polynomial or exponential, and I'll tell you a whole lot about this problem. So again, just to emphasize this problem again, so you have a deletion channel. So you have some n-bit message where each bit gets IID deleted with probability some constant, say half. And you want to distinguish whether X is being sent to the channel or if Y is being sent to the channel. This is analogous to the reconstruction problem where some unknown n-bit string gets sent through the channel and you want to reconstruct the n-bit string after some amount of traces. But up to polynomial factors, the answer to the reconstruction problem is the same as the distinguishing problem. So this just makes it simple. Yeah.
Sorry, I'm getting when you say one, it means constant.
Oh, so one trace suffices to get constant success probability.
Okay. And then you assume P is constant.
P is constant, yeah. Yeah. Yes. Yeah. Yes.
Suppose I have two string, one of them is in the middle point, has a one and everything else is zero, and the other one has a one left of that, right? Okay, position n/2 and n/2 minus.
Okay, so consider the string which is all zeros except for one at position n/2 in X versus the string Y has a one at position n/2 plus one.
Yes. Okay. First you need to
N.
distinguish. You can do it with n.
Yeah. With constant probability, you will see one of the two. Sorry, with constant probability, the one in the center will appear. It'll appear in a binomial distribution, which is roughly a Gaussian distribution, roughly a Gaussian distribution of width root n. Okay, so how do you distinguish a distribution of mean n/2 versus mean n/2 plus 1 given something with variance n? It takes roughly n samples. Okay, so this is a n lower bound, which is surprisingly close to the known lower bound of n3 halves. You almost already won the game, almost. Okay. Okay, so does that help? Okay. So we want to carefully construct the hardest to distinguish strings X and Y to make trace reconstruction hard, or come up with an algorithm that will win in all cases. Okay. Okay, so trace reconstruction, frequently asked questions. I don't know if these questions are frequently asked because I haven't given this talk enough, so I just came up with a few. But feel free to ask more questions. So this is just a few obvious things to ask and a few just classic, interesting points to be aware of here. So what's the case for random inputs? So how hard is it to distinguish a random X from a random Y? So here it's actually sublinear. So e to the log to the 1/5 of n, so this is way below n. Okay? So for random inputs, this problem becomes really easy. This is an upper bound.
Random meaning like uniformly random?
Yeah.
Okay.
Yeah. What is the optimal algorithm for trace reconstruction? It is maximum likelihood. Okay, so you either are looking at traces from X or traces from Y. What should you do? You just figure out which one is more likely. We know what the optimal algorithm is. We just don't know how to analyze it. Okay. And yeah, you can do this in polynomial time. There's a dynamic programming way of figuring out the probability. Okay. What's the hardest known case? So it's not actually putting a 1 at n over 2 versus 1 at n over 2 plus 1. It's doing that in this string, the 0, 1 string. Okay. So this is just a tiny variant of Sapir's suggestion. So take the 1, 0, 1, 0, 1, 0 string and add a 1 either in the middle or 1 to the right. Okay. So this is the hardest known case to distinguish. This is the n to the 3 halves lower bound. Okay.
Roughly why it is n plus 3 now? Or even just by its part. Yeah.
So in the case you suggested, there's a single one and that's distributed with some noise around the middle, and you just need to take many samples from this and figure out the average location of the one. But here, there's no longer a single one to look for. Like there is a single one, but it's buried in a sea of even more noise.
There's a one here, right? And it's probably 1/4, there's a 1 here.
Oh, okay. So yeah. Okay. So after you insert another one, there will be a double one pair, which looks like it'll stand out. But after feeding this through the deletion channel, lots of bits will get deleted, and there'll be lots of. Okay, so just to spoil something, which I was going to mention a bit later. So a different way of looking at this, instead of thinking of inserting a one, think of this as having an extra 0, 1 pair, and we're either deleting a 0 from here or deleting a 0 from here. Okay, so I promise you we're deleting a 0 either from here or from one space to the left. But then we're also deleting a huge number of other zeros. So the extra deletion is going to be hidden in a sea of other deletions. So we're both trying to find the location of the extra deletion. Sorry, we're trying to find the location of the extra deletion, but we're buried by two different things. First of all, the location that this deletion ends up at is going to be randomized. And second of all, it'll be hidden by the presence of many other surrounding deletions. These two effects add up to give this n to 3 halves bound. Yeah, fair, intuitive question to ask. Okay, next frequently asked question. What's a natural, fully characterized algorithm? And it's called mean-based statistics. So it's the following. Look at the following statistics from a whole bunch of traces. Take a whole bunch of traces, and then for each location I, ask what's the mean value of bit I in the trace. Okay? So this is kind of like a statistical query algorithm. So just for each different location I, independently average across all the traces. Don't try and do any correlations within traces, just average across all traces. So take the mean of all the different locations in all the different traces and return this, for each different location. What can you learn from this? So it turns out that we've got matching upper and lower bounds saying that if this is all you can do with your data, then it takes e to the n to the 1/3 traces to distinguish things, and also there's a matching lower bound.
So jth bit is the jth bit in the trace.
Yeah, sorry, yes.
That could actually correspond to very different things.
Yeah. But this is again an elementary and natural thing to do with the traces. Given a whole bunch of traces, what do? Let's just take the means of columns of our input matrix essentially, and then do what we can with that. What can we do with that? We can do e to the n to the 1/3 with that. Okay. Okay, the fanciest fully characterized algorithm is, so this is a kind of statistical query thing where we just statistically ask what's the expected value of various different statistics. In this case, just 1-bit statistics. We can ask about much more complicated statistics. Instead of just single bits, let's ask about n to the 1/5 contiguous sets of bits. So you can compute any statistic you want on any n to the 1/5 contiguous set of bits. Compute all these things, do anything you want with all these things. This manages to improve the situation to e to the n of the 1/5, which again matches the current best upper bound for the whole problem. Okay. So this is pretty general, pretty fancy, yeah. And the last thing on this, okay, sorry. But okay, at some level, this is a bit less impressive because the proof technique is just a mean-based analysis based on strings that only have 1 every n to the 1/5 locations. So your statistical query that learns all the information about an entire contiguous segment of length n to the 1/5 is actually only as finding the location of a single one. Okay, and finally, what's the stupidest algorithm that we don't know how to characterize? So as opposed to mean-based statistics, just pairwise statistics, what's the value of the jth bit times the kth bit? Okay, so if you just do the obvious second order thing as opposed to first order thing, we really don't know what's going on with this. I might guess off the record that it's e to the n to the 1/7, which would be better than the best known algorithm. Why 1/7? Don't ask me, and I don't have any good reason for this, but it's just, yeah. So this talk is actually going to focus on low order statistics like this. And there's a lot I can say about this. I can't answer this question, but I think it's a really promising direction to look, and we really don't understand what's going on with it. Okay. Yeah, question?
The hardest known case, do we have an algorithm as well, or is that?
Oh, yeah, for that particular case, the analysis is tight. Yeah.
So it is, and
Yeah.
we have other candidates for even first. All right.
Wait half an hour. But yeah. Before today we did not. Yeah. So yeah, the lower bound has resisted a lot of efforts. A lot of people are conjecturing that the lower bound is fairly tight, which is a surprising conjecture and a strong conjecture, given that the upper bound is exponentially far. But yeah, like the fact that the lower band has resisted so much work is somehow viewed as a stronger signal than the upper band side. So I was going to say something else. Yeah. Oh, yeah. Okay. Yes. Okay. No. Okay. So I'm going to change pace a little bit and just tell you guys some cool techniques and things. But so why am I interested in this question? So at a super high level, I like looking for these subtle statistical signals. So this is one of these problems where we just don't even really know what to look for. So one buzzword that I've been trying to get people to use since my PhD, and I think it's finally caught on, is data efficiency. So data efficient algorithms. What's the best way to use data? So in any kind of algorithms course, you learn these techniques for optimizing your algorithm. It's usually optimizing the time complexity or optimizing the space complexity. But these days, like for most real companies trying to get things done, it's data that's the limiting factor, not time or space. So trying to get algorithms that make the best use of their data, I think is just a really fun research thing that I've been spending a lot of my research time researching in various different guises. And this is another one of these things where just the question is, where are the statistical signals to figure out what's X versus Y here? And we really don't know where to look. Yeah.
Sorry, this is a bit of to what you're saying, but if I ask a more fine-grained question that, so I give you X and Y and I'm looking at how many traces I need as a function of sort of the distance between X and Y.
Oh, yeah. That's a really good question. Sorry, so I don't know the answers to this. So I think there's good fine-grained results. I can't give you the citation, I mean, but so based on like n to the power of the edit distance between the two strings, which is stronger than the Hamming distance. So for two strings that are extremely close, we know things can't be too bad. Intuitively, as the edit distance increases, two strings intuitively get easier to tell apart. But we can't prove that there aren't two strings that are really different in a complicated way, but that really obfuscates the way that they're different from each other. So I maybe for mean-based statistics, you mean? Yeah. Yeah. So there are upper bounds for low edit distance, and I guess lower bounds for mean-based statistics for low edit distance. But yeah. Okay, so all right, this is mostly an unrelated slide that I just wanted to include just because I think it's a fun idea. I've included a few just fun ideas here. So what makes this problem hard? One thing which makes this problem hard is something which also makes robotics hard. And because I'm betting most of you guys aren't robotics people, I get to explain SLAM to you. Who knows what SLAM is? Great. Okay. So yeah, I'm sure you could probably explain this better than me, but so like SLAM is this classic robotics task where you have a robot and it both doesn't know where it is and it doesn't have a map of its environment. Okay, you throw a robot in a new room, it needs to both get around. So it needs to get around, but to get around, it would be nice if it had a map. It also would be nice if it knew where it was going. And this is kind of a chicken and the egg problem. So you want to do these two tasks, and if you could do either one, it would help you do the other. So, okay, supposing you knew your location really well. Sorry, yeah, if you knew your location, then you could just take a picture of the ground underneath you and start building a map. So I took a picture of the ground underneath me. I know my location, so I just start building a map. I just write the square over there. Sorry, okay, I've forgotten the order of my slides. The other direction, if you have a map, you can find your location by just taking a picture of the ground and comparing it to the map and finding where in the map that matches up to. Okay, yeah, and vice versa. If you know where you are, you take a picture of the ground and just edit it into the map to make a map that way. Okay. But if you have neither your location nor a map, then how do you do this? And this is a very real problem that robots need to deal with. Okay, so yeah, sorry. Okay. What makes this hard? Well, one thing which makes this hard, and one thing which is kind of characteristic of the trace reconstruction problem, is if many different parts of your map look similar. So one way of describing where to go on a map might be, find the location with a palm tree. See, there's two palm trees just appeared there. So last time I gave this portion of the talk, I was in San Diego, and go to the palm tree sounds like great directions. But in San Diego, there's like literally thousands of palm trees everywhere. So like that, even if you know there's palm trees where you are, that doesn't help you disambiguate various different locations. So it's the same thing with the trace reconstruction problem, that if this is the location that you are, I'm looking up underneath me and this is what I see, then where in the string could this have come from? Many different places. And if this is the original string X and you're allowing X to be partially deleted, then there's even more places in X that could, when partially deleted, lead to this. Yeah. So you're both trying to figure out the map, like am I looking at X or Y, and you're trying to figure out your location in the map at the same time. And these problems mutually reinforce each other just to make your life hard. So this is one thing which is hard about the trace reconstruction problem, which is not hard about the other channels, which I started this talk with, where your location stays fixed. So simultaneous localization and mapping. This is a robotics problem, but also one view of the root of the hardness of trace reconstruction. Okay. So if you guys hear this term anywhere, like I hope you guys will remember it because it's just a cool thing to be aware of, just a real world problem that we're still wrestling with all the time. Yeah.
Because this is now just like going at a corner, what do robotics do?
I mean, it depends on the robots. Like they have lots of physical constraints about what they can explore, and they've got lots of constraints on the type of map they're looking for. If you have any constraints about the shape of the environment, that could help you as well. If you know your environment is rectilinear, that helps. If you don't know your environment is rectilinear, you could lose track of absolute orientation as well and things like that. Yeah, it depends on the constraints that you have. But Google this. There's a huge Wikipedia page on this. It's a major line of research. I can't summarize this. Okay. So yeah, okay, sorry. I've got way too many things to talk about to fit in an hour, so I may skip some stuff. But lots of people have been trying to find some kind of coding theory approach to coming up with lower bounds for trace reconstruction, where kind of we intuitively suspect that repeating substructure makes this problem hard. And how do you embed repeating substructure? Well, with some recursive code. I don't think anyone's been able to formalize this, but it's something very tempting. Yeah, and again, the best thing we have is still the 0, 1, 0, 1, 0, 1 pattern. Okay, so what do you do if you can't solve a problem? And this is kind of advice to the grad students here as well. Well, you can change the problem. And changing the problem is totally fine. It can help you discover new things. It can even help you discover new things about the original problem, which if we have time to in this talk, we'll get back to. Okay, let me tell you about circular trace reconstruction. So supposing the string is a circle instead of a linear string. So we now, again, delete bits IID. So we now get a shorter circle. And then we can unwrap the resulting circle in many different ways. So you can view this as just taking a random cyclic shift of the trace after you delete. And there's even some motivation here. Bacteria has circular DNA. And in the million years since some common ancestor, we may see many traces of the DNA from a million years ago, many descendants of this bacteria. And evolution has mutated DNA, so things have been deleted. And of course, it's a circular DNA, so we have no notion of absolute offset. So how can we reconstruct evolutionary history given current bacteria that we can observe? Yeah. So is circular trace reconstruction better or worse motivated than the original problem? I think they're both, first-class problems that we should, we deserve to know the answer to. So it's provably at least as hard as the original problem, just because there's kind of one additional layer of confusion added by just a random cyclic shift. Best known prior lower bound for this was n cubed compared to the n to 3 halves for linear trace reconstruction. The best known, the instance of the best known lower bound is actually a bit simpler, perhaps. So let me just define a representation for sparse strings. So I'm going to have ones separated by big C's of zeros, and I'm just going to count the length of each stretch of zeros. X1 is going to be the length of the first stretch of zeros, X2 the length of the second stretch of zeros, etc. Okay. And if I go X1 up to Xk, then there's K ones in my string maybe. So the indistinguishable pair for the lower bound here is you have some big common offset and you add to it either 0, 1, 2 or 0, 2, 1. Okay. So these are different strings. They're not cyclically identical strings, but they can easily be confused for each other if you delete things and also cyclically permute things. Okay. So a summary of the proof, again, it's not the analysis, but just kind of one of the key steps is that, so as it turns out, kind of second order statistics of these gap strings turn out to be the same. So like x1, x2 plus x2, x3 plus x3, x1 is the same for these two strings. And there's only third order statistics, like these strings are the same at first order, they've got the same elements, they're the same at second order, they vary at third order, and this is somehow why we get an n cubed lower bound for this. Okay, let's talk about this more generally. I want to kind of generalize this proof technique until we get something more abstract and principled, and then maybe we'll bring this back to non-circular trace reconstruction later. Okay. A natural mth order statistic is just a monomial of order m. So just multiply m different locations, xi1, xi2, up to xim. And the indices might not be identical. I might take like x1 cubed times x7. That would be a fourth order statistic. And because this whole problem is cyclically symmetric, I kind of want to symmetrize things that I'm not looking at spurious information. So I'm just going to sum up overall cyclic permutations of this. Okay. So a way of describing this thing in this new language is that these strings x and y are distinguishable by third order statistics, but not second order statistics. Okay. So symmetric third order statistics, these strings are distinguishable, but any second order statistic you pick, anything you pick, they're the same. And under the hood, this is how the published proof from 5 years ago shows that you have an n cubed lower bound. Okay. Okay. In the next slide, I'm going to briefly summarize a whole bunch of complicated and interlocking results about cyclic statistics that lead to new bounds for circular trace reconstruction. I won't prove any of this stuff, but I want to both emphasize the cool ways that everything interconnects and also just use this as a way of advertising that these low order statistics are kind of the right way of looking at this and might be the right way of looking at the original problem, which we'll get to in a moment. Okay, so result number one. The probability of, okay, so you input some string with certain gaps, and then you get out a string with certain gaps. Of course, some of the ones may be deleted, so you might have fewer gaps. In this case, we're looking at strings with a constant number of ones. So there's going to be a constant probability that none of the ones are deleted. And that's what I'm going to analyze on this slide, okay? So if none of the ones are deleted, you get some string with some certain gaps. And what's the probability distribution of getting a certain string of gaps? Well, as it turns out, it can be represented in terms of cyclic statistics of the original gaps, okay? So some degree k polynomial whose degree k minus m coefficient is roughly, there's an asterisk here, something about the order m cyclic statistics of x. Okay, so the highest order term is predictable. The k minus 1 order term depends on the first order statistics. K minus 2 order term depends on the second order statistics, etc. Okay, so to highest order, if cyclic statistics match to the first several orders, then all these probabilities match to the first several orders, which is kind of suggestive. Okay, and then on the flip side, algorithmically, what can we do with these statistics? Well, we can estimate an order n cyclic statistic using roughly nvm traces. So this is kind of the upper and lower bound side of this characterization here, saying that cyclic statistics really do tell you what's going on here. How hard is it to so like how much can you match cyclic statistics? How confused can you get with cyclic statistics? So MATLAB found some strings which have identical statistics up to order 4. So they differ at order 5 and above maybe, but up to order 4, they're totally matching. Okay, so these are strings of order 12 whose cyclic statistics match up to order 4. Okay, so again, these are sequences of gaps. Okay, so this describes a sequence with 12 ones, and the gaps are n plus 2, n plus 3, n plus 2, n plus 1, that kind of thing, in one string versus whatever the gaps are in the other string. Okay, and this is, slightly less motivated, but in terms of the nth order cyclic statistics, you can also somehow express m tuples of Fourier transform of the trace locations. Okay, so this is relating cyclic statistics of the gaps in the original string to Fourier transform m order statistics of the trace. And for reasons which I cannot begin to explain, we can use this to set up certain equations where certain 6 tuples of equations let us derive uniqueness. Let's actually solve for the original gaps. So this shows a uniqueness result that if phrasing the yellow thing in the contrapositive, if 2 sequences have the same cyclic statistics up to order 6, then they actually need to be the same, or just a shift of each other. So putting these pieces together really fills out the whole story. So the first 2 results combined say that we need n to the fifth traces to distinguish these two strings. Okay, so these are two strings that match all the way up to fourth order and only differ at fifth order. And then this is saying that their probabilities of being observed must match up to fifth order. So there's only a n to minus fifth signal in the any probability that you observe. These two things in combination are basically an if and only if characterization. So yeah, the asterisk here is from the asterisk here that the function also depends on the permutation. Sorry, it depends on the elements of the gaps. So this lower bound weirdly kind of only holds if x and y are permutations of each other. Though if they're not permutations of each other, they should be even easier to distinguish, but we can't prove that. So this is an if and only if characterization, basically, up the asterisk, saying that they can be distinguished in n to the c circular traces if and only if they have a cyclic statistic that differs of order c. Okay, so if you figure out where they differ where they first differ in a cyclic statistic, that tells you exactly how hard they are to distinguish. Okay, again, this is sequences of the form 1 followed by a bunch of zeros, followed by 1 followed by a bunch of zeros, with just a small number of ones. These last two results, so saying that we can actually algorithmically estimate stuff, combined with the whole thing that any two things that differ must differ in order 6, says that we can actually distinguish anything in order n to the 6th. So combining the first and last thing, this is the n to the 5th lower bound for the sparse case of circular trace reconstruction, and n to the 6th upper bound. Okay. Again, sparse circular trace reconstruction. But the lower bound is a lower bound, so this is a new lower bound for the circular trace reconstruction problem. Again, the previous lower bound for circular trace reconstruction was this n cubed thing, which under the hood was relying on third order statistics. But then we've kind of revealed that these lower order statistics are the reason for that paper succeeding, and then we've extended this to fifth order statistics and shown that you can't extend it beyond 6 to get a new lower bound, and then reasons why this lower bound is actually as good as we can get up to 1. Right, question? Yes. So this characterization only works for sparse strings. Though, yeah.
Like the number of zeros separate, the gaps are small.
Yeah, so again, this lower bound is saying that here are two sparse strings that are really hard to distinguish. So that lower bound just holds. But to algorithmically use statistics to identify the strings, this only works for the sparse strings. Okay.
Sorry, how does it depend on the sparsity parameter? Like,
badly. Yeah, I'm just assuming that there's only a constant number of ones. Because that's all we need for this example here. So there's just 12 ones. Yeah. So okay, of course you're wondering about sparse things in general, and I'll tell you that in a moment, okay? Yes.
So do you know that the statement that you wrote would be false if the strings were not sparse?
Sorry, which statement? There's many statements.
He took distinct x, y differ in some.
Oh. So I think maybe you could show that they differ, but then the algorithmic side of distinguishing them, I'm not sure if you could do that. So really,
So you're saying
Yeah.
even if they differ in some cyclic statistic or order less than 106, if they're not sparse, I'm not sure how to use it.
yeah. Yeah. So yeah, there should be the word sparse here. There should be the word sparse implicitly everywhere in the slide, because this paper was about sparse strings. Yeah, this thing is certainly for sparse strings. Everything here is for sparse strings, but I think this is the thing that fails for dense strings. Though, yeah, I'm not. We didn't try proving this for dense strings, but I think the yellow thing might work for dense strings. It's just not useful yet. Okay, so I hope this motivates low order statistics as a thing to start asking about in general. And yeah, Santashini? Yeah, okay. Has asked about applying this in general, and yes, I want to ask this question too. So let me try and tell you about trying to apply any of the previous intuition in the original setting of trace reconstruction. Okay. Okay, so again, the natural M-order statistic of the trace is just you look at the product of m different locations in the trace. And well, okay, I guess here the locations probably should be distinct because they're just zeros and ones. Okay, again, we're now considering it in a non-cyclic setting. You have some sparse string, what happens? Okay, actually, there's a paper saying that this is quite easy to deal with and not interesting. Sorry, it's interesting, but not interesting in the, like, none of the interesting stuff from the previous slide even applies here because it's can be solved via totally different ways. Okay, so let me tell you about that briefly. Sparse trace reconstruction is easy. So this is a paper from last year by Aman Liu and Narayanan. So it works in surprising generality. So as long as the ones are always separated by at least polylog n, like n polylog like log to the 8th n, then you can always I think this isn't even distinguishing. I think this is fully reconstructing the strings. I think. And n log n traces polynomial time. I forget. Yeah, I'm not sure the time. This is shockingly effective and way better than we could do in the cyclic case. So how does it work? Okay. Well, just the linear case has a lot of structure that the cyclic case doesn't because you know where things start. Okay, a 1 at location n over 2 in the input, I just pick something in the middle of the string, we'll end up at some location. So supposing P is your retention probability, like 1 minus the deletion probability. So then if you start at location n over 2, each bit will get IID deleted and will be IID retained with probability P. So the location this ends up at is just going to be binomial distribution n over 2 pointless of bias. Okay. So it'll end up at that location, and the kind of blur, the uncertainty in its location will be roughly the square root of its location. Yeah. Times a P, but you know that P is a constant. So that's a lot of blur. Like n over 2 is, sorry, square root n over 2 is pretty big. It's certainly bigger than polylog. But we have something even better to work with. 2 ones that are closely spaced to each other, 2 ones location G apart. Well, let's look at just the deletions in between these 2 locations. So this is just binomial of G comma P. So if 2 things start G apart, then the relative uncertainty in the trace will end up being just square root of G. Okay, so things that start close together, we get really high resolution insight into them in the trace. Okay, and so this is enough to get an algorithm. Okay, if we have a gap that's bigger than polylog n, we'll basically never confuse G with 2G with 3G. Like even if you add plus or minus root G to these things times even a polylog thing, you'll still never confuse 1 gap with 2 gaps with 3 gaps. So it takes a lot of combinatorial trickery and stuff to actually get this into an algorithm, because there's lots of cases. They prove this in impressive generality. But still, the fact remains that even given 1 trace, we can learn a surprising amount about what's going on, because we're just never going to confuse this gap for a gap that's like, it's like a gap between 2 nearby ones. We're kind of never going to confuse between a gap of that plus another polylog n thing. So yeah, they brought some algorithm that says that an iterative algorithm. So if you know the location of the first m1s in the input, then given just 1 more trace, you can, with some constant probability, find the one that comes from the next location in the input. Okay, so there's somehow just overwhelming statistical signal here. So So the statistical signals are somehow way stronger for sparse strings in the linear case than in the cyclic case. And there's no need to combine weak mth order statistics and do anything complicated like that. Just one trace suffices. There's no statistics here. Okay. Okay, but I want to do statistics. Okay. Let's try a variant of this. Instead of sparse strings, I'm going to try not sparse strings. So instead of one separated by c's of zeros, I'm going to have one separated by c's of 0, 1s. So sorry for this purple insertion here, but one followed by 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and then another one. So there's like a pair of ones here, and then 0, 1, 0, 1, 0, 1. Okay. So the same kind of thing, except instead of c's of zeros, it's now c's of 0, 1s. And it's a lot easier to get lost in the sea of zeros and ones because the ones don't stand out nearly as much anymore. Okay. Okay. Inserting a 1 into a sea of zeros and ones. What do traces from this kind of thing look like? So I've changed notation slightly. 0, 1 to the A1 means 0, 1 repeated A1 times, followed by 1, followed by 0, 1 repeated to A2 times. What do traces look like like? So as I mentioned at the beginning of this talk in response to a question, a different perspective is that instead of thinking of this as inserting ones, it's like deleting zeros from a slightly longer string. So start with 0, 1 with a few more 0, 1s, and then we can generate this this string up there by deleting the A1 plus first 0, and then also the A1 plus A2 plus 2th 0, et cetera, et cetera. So this is just the same process with deletions instead of insertions. And then feed this through the deletion channel. And the point is that we're making a few extra deletions here, but in a sea of many, many other deletions. And statistically, this deletion looks like any other deletion. Like we're starting out with a very regular string, making a few sparsely spaced deletions, and then making many, many other deletions that are very dense. So we're not going to be able to figure out what came from what. So different way of saying this is that given a trace, if we see 0, 0 consecutively, we know that something was deleted in between them. So we can detect deletions. We can't detect all the deletions. Like if there's a 0 and a 1, maybe there's no deletions, or maybe there's 2 bits deleted, or 4 bits deleted, or 6 bits deleted. But we can detect some deletions. So the trace tells us some of the deletions with their positions blurred. So adding one more deletion in these certain locations leads to a slight local excess in expected observed deletions. We're adding one more deletion in some location that will end up being blurred by some amount like square root of n. Okay. If we do several of these blue deletions, then we'll end up with several overlapping, possibly bumps of excess deletions. Okay. And the challenge is the challenge on the lower bound side is to design two different sequences like this that are very hard to distinguish, or on the upper bound side, the challenge is to distinguish them, So how can we distinguish them? So the mean-based statistics will tell us the expected value of this curve. Second order statistics are looking for pairs of deletions. Okay, so how can we get lower bounds? Okay, so I've slightly changed what's written up top. So it's now 0, 1 to the g plus a1. I'm going to have some common big gap, and then think of a1 now as being just some small modification. So standard lower bound idea, I want to construct two different sequences, A and A prime, that describe indistinguishable mixtures of bumps. So A is going to be one thing, A prime is going to be something pretty nearby, but different. But then when you feed them all through the trace process, they look really hard to distinguish. So to fool first order statistics, we just need the expected number of deletions at each location to match in A and A prime. Okay, so this is a question for you guys. How can I find two different mixtures of the same width bumps? I'll call these Gaussians, or they're actually binomials, but how can I find mixtures of, say, Gaussians, two different mixtures of Gaussians that really, really look identical? So for any of the maybe grad students in the room, do you know how to find mixtures of same width Gaussians that look the same? guess a different way of saying this is that you have two different functions that if you blur them out by a huge amount, they look the same. Like blurring really should lose information. So by pigeonhole, there should be just tons of ways to get fooled by a blurred version of your function. Okay, I love Gaussians. They're one of my favorite tools to work with. And even when you don't have Gaussians, it's still my favorite tools to work with because you can blur your eyes and everything starts looking like a Gaussian if you squint hard enough. But okay, so one way of doing this is just alternating binomial coefficients. So one sequence is the even locations of a binomial distribution. The other sequence is the odd locations of a binomial distribution. If you blur these out by something like the width of the binomial, then they'll be exponentially close to each other. Okay, fair. Okay, even harder question. This is actually hard. So I'm not allowed arbitrary coefficients here. I'm just allowed integer locations, and at each integer location, I'm just adding one deletion. So I now need two binary sequences whose blurs are very hard to figure out. Okay, this is much harder than just, yeah. Okay, does anyone know the name of this question? Sort of. So sorry, Terry, yeah, well, okay, we don't know the pronunciation. Classic combinatorics problem. Elena's written papers on this as well. Okay, so you can do this. You can get fairly short sequences that match to pretty high order. And these things exist by the pigeonhole principle, but if you actually want to explicitly find them, then it's a famous known problem to find explicit constructions for something that, whose existence is guaranteed by pigeonhole. Okay. This makes the expected number of deletions at each location really match as close as you want. But there's also second order statistics and third order statistics. So if we want to get a lower band, how do we get the higher order stuff to match? Well, okay, the easiest silly thing we can do is let A prime be negative A. And then any second order thing we do is going to be the same by parity. Okay. Third order statistics, I don't know about, they'll disagree, whatever. But yeah, so this is already enough for something. So I let A be some Fourier-based sequence, which you can find by pigeonhole on a computer easily, and let A prime be negative A, and these describe sequences of gaps. And then there'll be really no signal at first order, exactly no signal at second order, something at third order, but third order is already pretty hard, it's a pretty weak signal. Okay, so let's run some code. Okay, I'm gonna end pretty soon. Sorry for holding you a couple minutes over. Run some code to actually try this. I don't actually have a proof for this yet, but running code is useful. This is code with error bars, but even with the error bars, it's still wiggling a little bit more than the error bars, So like, this is a complicated phenomenon, which is maybe why we haven't managed to prove it. One parameter is how much we're spacing things. So I don't know how to pick this. So I've tried all different values of spacing, and then try different values of n. And then the hope is that as n increases, so as you go down these lines, the best counterexample you find, the minimum of these curves, is going to decay faster than n to the 3/2, which is the best known lower bound. Okay. And I'm computing the squared Fourier distance, and 1 over that is the number of samples you need, a lower bound. Okay. And I just want to mention, I didn't actually know how to compute these numerics, so I just want to briefly explain the numerics because, I think we sometimes take numerics for granted, but there's often A, some thought involved, and B, some actual coding involved. So yeah, let me just explain the thought part of this. So, okay, what is this a graph of? So given a proposed counterexample pair x and y, I want to estimate the number of traces needed to distinguish x from y. And a bound on this is just the 1 over the squared Fourier distance of the probability distribution of traces from x versus traces from y. Okay. sorry, for those of you who haven't seen squared Hellinger distance, it's something that is subadditive on product distributions, so that if I've got a bound on the Hellinger distance of one sample, then I know that a million samples, I'll only get a million times much information, so that in order to distinguish these things with constant probability, I need the Hellinger distance to be a constant big. And I know that if the squared Hellinger distance is, say, 10 to the minus 10, and I need it to be a constant big to win, and it is subadditive on product distributions, then I need to repeat this process at least 10 to the 10 times to get up near 1. Okay? Okay, so how do I do this? How do we numerically estimate this? I'm just going to describe this for the simpler total variation distance, though once you see the algebra, it'll be totally obvious what to do. Okay, total variation distance. So sum overall, this is notation people use for traces. Sum over all possible domain elements of the difference between the probability of getting this from distribution 1 versus distribution 2. Again, this is just a definition of total variance. Let me rewrite this as a by pulling a key outside this, so p times as value 1 minus this. Okay, haven't done anything. Now, sum of p times sum of the probability I can rewrite as an expectation. This is an expectation of just the thing inside the absolute value. Okay, and I can compute this by sampling. So here I sample its face from say x, and then for each trace, I compute this thing, which is 1 minus the ratio of the probability of getting that trace from the second string versus the first string. Okay, and I can figure out each of these things by dynamic programming in quadratic time. This value is roughly around 1, so roughly it's going to be bounded, so you won't have any variance issues. Although it actually isn't bounded because you might have to divide by 0 things, so you can do further things to sample from both p and q and modify this function so that the expectation is the same, but the variance is reduced. So there's a lot of numerical stuff you can do. I spent a lot of time writing code for this. I even broke up the old graphics card and wrote some CUDA code, which I'm sure none of you guys have tried doing. But yeah, so this is a big computation, like 2.5 million things. It's quadratic time dynamic programming. You need to run this 100 times to get some good statistical concentration. And then I tried this for all these different values of spacing and everything. So it takes some effort to do this. Yeah.
I think if you want to go to Hellinger, I mean, what you would have liked is just conductivity of the whole thing. You're saying I'll go to Hellinger distance because it gives me some sort of additive structure.
Exactly. Yeah.
But and if you're computing like this, I mean, KLR just gives you a perfect chain rule, and then
yeah, I'm pretty sure we could have used KL distance as well. Yeah, KL distance and Hellinger distance are pretty similar, except one is bounded, the other isn't.
I see, but and then you eventually pay a gap of like mean square or something, and you're saying
which is a constant. Constant, yeah. So you could have done this with KL distance, yeah.
I'm doing it for TVDs. The loss is really bad with overrun samples.
Yeah, you would get the square root of the bounds here. So yeah, you don't want to pay square root. Yeah, so Kale and squared Hellinger are really good about adding on product distributions, whereas TV does not. Yeah. Okay, so yeah, so if you actually compute the slope, this is somewhere around 1 over n squared. I won't say exactly if it's n squared or not, but it's somewhere around there. Oh, and yeah, the exact sequence I used is some thing that matches up to like 5th order or something like that. And yeah, okay, so sorry, I'll go over this very briefly. This is my second to last slide. So I just talked about lower bounds, but looking at this, I think is also really useful from an algorithmic perspective. Dramatically different from the sparse trace reconstruction in this published paper, it seems like low order statistics are the only signal here. Like this, these deletions really get clobbered by the other deletions. The signal is followed by the noise. All you can do is try and look at very subtle distant correlations between multiple deletions. Um, so from an algorithmic side, the fact that this is such a specific case with 0 ones in between each of the ones, I think you should view this as being indicative of a more general phenomenon. So even if you take an arbitrary string and insert ones at alternate locations into it, this still has a clear low order signal. So if you insert a one before a certain string versus after a certain string, then the average location of ones in that string is going to move to the right. Unless the string in the middle is all ones, in which case adding one before or after is literally the same thing. So of course you can't distinguish them. Adding a one into some background string, even if it's not 0 ones, still has this flavor of inducing low order statistics. And the trace process, of course, changes this region to be some other more blurred out region. And the regions might overlap. And you might need to look at multiple regions at once because they start overlapping. Low order statistics of the trace correspond to low order statistics of the offsets. So this really suggests that looking at low order statistics is kind of the only thing you can do here, but it's actually surprisingly general. I mean, in some limit, like any two strings you want are kind of like insertions of ones at some way in some background string. Like, if you just insert at all the locations into two different strings, then you can kind of represent the whole trace process in this way. So these kind of strings remove all other avenues of attack other than low order statistics, but also really suggest low order statistics as a new and general approach for this. Okay, so conclusions, extra thoughts. So yeah, low order statistics exactly characterize circular trace reconstruction for sparse strings, which gives us 5th order lower bounds and 6th order upper bounds in the circular setting for sparse strings. And deletions in this complicated background seem to emulate some aspects of the circular setting in the linear setting. So lower order statistics seem to be the tool for both upper and lower bounds in this setting. So it seems like we can get maybe an n squared lower bound, though haven't been able to prove this yet, just numerics. And n squared is ridiculously far from the best algorithms that we know, but people are starting to suspect that this might be roughly around where the ground truth is. If 2 is right exponent, does this mean second order statistics are the answer? Actually, no. Unlike for the circular sparse setting, the order actually is not the same as power band. And I don't actually think any constant order statistics will be sufficient, but still I think this is the tool to start looking at. So yeah, that's it. Sorry for going over. Thank you. And I'm more than happy to talk to any of you afterwards as well. Yeah.
Okay, in real that period, what's n the maximum on Earth? No.
A million?
Okay, so it goes the order of the numbers, okay. Another and it related question is suppose you go to a planet where DNA is not necessarily a string or a circle, but in fact a more topologically complex object. This is the natural.
Yeah, yes. So the motivation for this question isn't any particular setting because there's so many different settings you can come up with.
Yeah.
But the fact that we can't solve even the most basic setting means we need to get better at math.
Yeah.
So
yeah.
So yeah, this is kind of a call to arms saying that this is a really basic statistical question where we kind of know what to look for, and it's obvious that there's such a big gap. We want to understand what to do here, and also in more general settings. This is just the simplest setting that I can point at and say it's just embarrassing our state of knowledge here. Okay, thank you.